Greetings and welcome. Today in our continued exploration of graphs of trigonometric functions, we're talking about the graphs of sine and cosine functions, which I suspect that up to this point you have not seen these or have not realized that you've seen these anyway. So they're going to be quite interesting functions, but before we get there, I want to talk about what a periodic function is and what I mean by the term period. Now here's the mathy, wordy definition for it, but I think it'll make more sense once I draw some pictures, or graphs more specifically. It says a function is periodic if, for some real number alpha, f of x plus alpha is equal to f of x for each x in the domain of f. Alright, so that sounds a little bit weird, but what they're saying is that if I have a graph where the y values repeat, completely, it's a repeatable graph for those y values, that function is then periodic, and what I mean by period is it is the least positive value of alpha for which f of x is equal to f of x plus alpha. That would be what I mean by the period. So let's consider what periodic functions might look like. So here's some examples of some periodic functions. Functions. Here we are. Yeah. There, that's a good enough O. So to draw some periodic functions, by the way, they don't always have to be kind of around the x-axis, but I'm going to have it for this sake, intents and purposes, it'll do. So let's see. Let's say I've got a function like this. This would be an example of a periodic function. And I've got like my cool Charlie Brown stripes here going on. And imagine that repeats that way, and it repeats that way. And it's just a repeating pattern, horizontally speaking. Alright, that the y values end up repeating for different values of x. Alright, so x values are changing, they're going all the way off to infinity, right, all the way over here, going forever, but the y values keep going through a cycle, alright, they are periodic. Alright, and so if I wanted to figure out whether or not this was periodic, what I would say is, for instance, this y value must repeat somewhere else in the function. And now what I want to point out is that, sure, this is a repeated y value where it hits that height a second time. However, this is not the period. Alright, this distance is not the value of p. If this was the period, the function would have looked like this. Alright, the next time that this repeats is all the way over here. Okay, because it's repeating this pattern, this whole cycle over and over, right? Here's another piece of it right there, right? So that would be the period right here. And if I had some tick marks on my axis, this distance would be that distance alpha, all right, is what that would be. And I want to point out that this period length is consistent between any two repeated points on my function. So for instance, if I went from here to, notice this is not where it's repeated, that is the same y value, but here this distance would be the same as that distance up there. And also likewise for maybe these low points right here. Alright, these are all the same distance that I've got going on. So this is a periodic function. Now in my case, I happen to have some kind of a little bit of a vertical pattern or symmetry to it as well, but technically you could have all sorts of interesting periodic functions. I don't like that line at all. There we are. That's a little better. I could have had a graph kind of like this, where maybe the top halves are, maybe I could have a steep line, steeper line down, and then I could have a circle, right, a semicircle. a line like that, a line like that, and then a semicircle, right? So I could have all sorts of interesting, weird behavior, and in this case, you could see the period goes from here to here. All right, that would be the period in that case, or from here to here, right? Anything like that. But just because the y value repeats, I just want to point out this is not the period, right? Also, if I had this pattern repeat a third time, I wouldn't want to go from this peak to the peak way over here, right? If I had repeated the pattern, this would be twice the period, right? It's gone through the cycle twice. I haven't found the shortest distance is what we talked about in this, right? The least positive value of alpha would be the period, right? So just because I can find it repeating all the way over here, maybe there was a simpler version of that pattern taking place. So yeah, you could have all sorts of intriguing shapes, and the reason I'm talking about periodic functions today is because it turns out that our sine and our cosine functions are also periodic, all right? That their y values or their outputs are going to repeat, okay? So thinking about the graph y equals sine of x, all right? X is going to be my angle that I'm inputting, and y is going to be the ratio that it's giving back. And we know that sine has repeated values, right? So for instance, sine of 30 degrees is equal to 1/2, right? Which is the same as sine of 150 degrees. But that doesn't mean that the period for the sine function is necessarily the difference between 150 and 30, all right? 120 in that case, because that could be one of these fake jumps, right? It could be maybe 130 to 150 is like a little jump like that for sine, and it's not truly that sort of thing. But why would you suspect, I guess, what do you know about angles and sine, or cosine for that matter, that would make you suspect that it's periodic? Think about any possible angles, right? Because sine, I could plug in small angles, or I could plug in really, really big angles, right? Like I could plug in what's sine of 1,000, for instance, right? Like I could have really large angles. What part of that makes you think that sine is going to be periodic? Well, sine repeats itself when we have coterminal angles, all right? I would expect sine to give me the same value for 0 degrees as it would give me for 360 degrees, as it would give me for 720 degrees, right? Or negative 1080 degrees, right? So coterminal angles is what's going to really cause the periodic nature for both sine and cosine, and tangent for that matter, and the trigonometric inverses, all right, which hopefully we'll get to this year. So it turns out sine is going to be a periodic function. So let's do an example where we're going to graph y equals sine of x, all right? And I just want to point out that x is going to represent an angle, and y is going to represent the output for my function is going to be the ratio. Okay? So for y equals sine of x, well, we're actually going to use radians today. And coterminal angles repeat every 360 degrees, right? If I add any multiple of 360, it's going to give me another coterminal angle. So in terms of radians, what's the equivalent of 360? 2 pi. So I actually expect that 2 pi is going to be the period for my sine function. Now, what's the highest value that sine gives me? What's the biggest number that sine gives me as a ratio? I know it's been a vacation since we've thought about some of this stuff. How high should I go for my y-axis if I'm graphing y equals sine x? Sine of 30 was 1/2, right? Sine of 45 was root 2 over 2. What's the biggest that my y-axis should go up to? You guys remember? Turns out the biggest it will go is 1, and the lowest it will go is -1. So I'm going to grab a little picture of this right here. And yeah, that'll do. And since for my inputs I'm going to be working in radians, I've got my axis labeled in radians here. Now, I had this generated for me by computer, but what I would typically do when graphing a periodic function like sine or cosine is I would go out as far as it's, the period, right? So I'm going from 0 to 2 pi. I'm expecting whatever's in here, right, whatever it's going to be, like whatever it's going to do, that it will repeat after that and it will repeat before that. So I'd start with 2 pi, and then I'll typically mark the tick mark that's half of that distance, so I'd mark pi, right? And then I would mark the tick mark that's half of pi, which is going to be pi over 2, right? Half of pi is pi over 2. So I might actually label this in this case. I can even label this in black. So here's pi over 2, right? Which is half of pi. Right? Does that make sense? Mm-hmm. And the distance that's halfway between pi and 2 pi is just going to be 3 times this. All right? Here's a quarter, here's 2 quarters, here's 3 quarters, here's 4 quarters, right? Sort of thing. So 3 of these, what's 3 times pi over 2? 3 pi over 2, exactly. All right? So I'd expect that to be 3 pi over 2. Right there.
It's not going up to 1 like the y-axis is.
No, it turns out for my inputs, I can go all the way to infinity and all the way to -infinity because of coterminal angles, right? We could find the sine of a 1,000-degree angle. We would just break it down into, an angle between 0 and 360 first. But yeah, you can plug in any values. It's the y values that are going to be between -1 and 1. And let's see, just so we're aware of what this tick mark is or this tick mark is, here's pi over 3. Half of pi over 3 is going to be pi over 6, right? And let's see, so this is going to be, this right here actually would end up being 5 pi over 6 because pi is the same as 6 pi over 6. All right, this one would be 7 pi over 6. And normally you wouldn't have to label all these, but since we're not super familiar with radians yet, I figured we might as well try to be, because I mean it's really radians, your familiarity with them is going to be as a result of knowing your fractions. Let's see, and this one's going to be another out of 6 pi's, but question, what would 2 pi be in terms of sixths? How many sixths is 2 pi? Yeah, 12 pi over 6 is the same as 2 pi, right? Because 12 divided by 6 is 2. So this one must be 1 pi over 6 less than that, or 11 pi over 6. Does that make sense? All right. I almost want to just like, when I write 11 pi, just like some sort of music note, I almost want to make it like 1 big pi. But that's not what it is. It's 11 pi over 6. There we go. So, all right. So there's our kind of x-axis. That's kind of the trickiest to do. Like I said, normally for these graphs, as you become more familiar with them, you'll be interested in just the maximum period. All right, half of that and then half of that, and then 3 times the quarter mark to get that. So you'll normally just need to break it up into quarters, and that will hit kind of your significant points for your sine and cosine functions. So let's make a table of values. Let's do this. And I'm going to make a table of values where I'm going to plug in some x's, and I'm going to do this horizontally just because of space. And I'm going to plug in numbers like pi, well, how about we plug in 0 first, 0 pi, then I'll plug in pi over 6, and then we'll plug in pi over 4. Plug in, bless you, pi over 3, and then we'll plug in pi over 2, and then we'll plug in, let's go all the way out to pi. All right, so that's only going to be half of our period, but I suspect that with our previous knowledge about sine, in which quadrants it's positive and negative in, we might be able to figure it out all the way to 2 pi as a result. So let's see, after pi over 2 in terms of sixths, let's see, yeah, then I'll have, 2 pi over 3, sorry. All right, and 2 pi over 3 is the same as 4 pi over 6, because pi over 2 is the same as 3 pi over 6. All right, getting used to these fractions here. Then we'll have the 5 pi over 6, and then we'll go all the way up to pi. All right, and pi, in terms of radians, is the same as what in degrees? Pi radians is how many degrees? 180 degrees, right? So it's halfway around our circle, our unit circle. So, all right, here we are. Now I've got this all set up. Let's see if we can make a table of values for this. So I'm finding out my y, my output, is going to be the trig ratio, all right, when I take sine of my x, all right? So sine of 0 radians. What is sine of 0 radians or degrees for that point? Does anyone remember? It's 0. Right? Sine of 0, if we're doing the hand trick, I'd put my thumb down. There's 0 fingers to the left of it. And I would, right, square root of 0, 0 divided by 2 is 0. Pi over 6, that's the same as my 30-degree finger, right? So this is going to be 1/2. Pi over 4, that's the same as a 45-degree, and that's going to be the square root of 2 over 2, right? Pi over 3 is the same as 60 degrees. Sine at 60 is root 3 over 2. Pi over 2 is the same as 90, right? Sine of 90, what's that? Square root of 4 over 2. Square root of 4 is 2. 2 divided by 2 is 1. So that's when sine is going to hit its maximum y value. All right, 2 pi over 3. I'm in quadrant 2 now. All right. So this is the same as a, what's that, 120-degree angle, is it? Not quite. It's actually going to be this value, because sine is still positive in this quadrant. My reference angle would actually be pi over 3, all right, in quadrant 2, and it's still positive. So this is actually going to be square root of 3 over 2. You know what? I forgot one here, guys. I forgot one. What one did I forget? Do you guys remember? I need the one that's symmetric to this one. 3 pi over 4. Wait a minute. Did I miss? No. Oh, my pi over 4 is landing there and here, I believe. So 3 pi over 4 I want to have because I had the pi over 4. And then I'll have the 5 pi over 6. And then pi. My apologies, friends. Yeah. Man, ugly line. There we go. So 3 pi over 4. That's a 135-degree angle, if you're thinking degrees. The reference angle is pi over 4. It's in the second quadrant, and sine is positive. So it should just be this value right here, root 2 over 2. Okay? 5 pi over 6, second quadrant, reference angle is pi over 6, so it's going to be positive a half. And let's see, sine at pi is 0. Okay, so you can kind of see it increase to 1 and then decrease back down to 0. Now the period is not pi, the period is 2 pi, because I expect that in the next quadrants 3 and 4, sine is going to have exactly these same values, except one thing's different. What's going to be different? They're going to be negative, exactly. Good job. So let's graph this. Let's see, I'm going to pick a darker purple here to graph this. Let's plot my points. So when I had 0, I had 0. Okay, so 0, 0. There we go. Pi over 6, I had a half. All right, wow, so this jumped up to 1/2 right away. All right. At pi over 4, which is halfway between pi over 6, or, well, it's half of pi over 2, which in my case is halfway between pi over 6 and pi over 3. It's root 2 over 2. The square root of 2 is 1.414, roughly. Dividing that by 2, I get 0.702, I think, if I recall. So this is, right here is going to be around 0.7-ish, a little bit bigger. 0.707, sorry, I think. I'm trying to remember. Square root of 3 over 2. Square root of 3 is 1.73-ish. Dividing that by 2, I believe I get 0.866, something like that. So between 0.8 and 0.9 is 0.866. And then at pi over 2, where is it? It's all the way up at 1. So at pi over 2, it maxes out at 1. And now it's going to repeat these values on the way down. So at 2 pi over 3, it's at the 0.866 again. Halfway between 2 pi over 3 and 5 pi over 6, it's going to be at the 0.7-ish. At 5 pi over 6, it's at the halfway mark. And then at this, it's at 0. All right, so looking at this graph so far, you can actually draw a smooth curve. Notice I said you can, apparently I can't. That passes through those points. It looks something like that. All right. Now what I want to point out about this curve is not circular. It's not a semicircle. This curve is not a parabola. All right, it doesn't hold that same shape. It's its own type of curve. It's a sine curve. All right. So I just want to kind of point that out. But if you kind of fill in those dots, you get that. Now, so this was, right, if I wanted to think about quadrants here, quadrant 1 was all here, between these values. Quadrant 2 is between here and here. Quadrant 3 would be between here and here. And quadrant 4 would be between here and here, right? So in these next two quadrants, it's going to give me the same values, just the negative versions of them. Okay? So I'm going to kind of, I guess, extrapolate these points here a little bit. So here at 7 pi over 6, instead of positive a half, I'm expecting it to be negative a half. Okay? And then it's going to drop down to the, instead of positive root 2 over 2, or 0.707, I'm expecting it to be negative 0.707. All right? And then halfway between these, it'll be the 0.866 thing, and then it will be at negative 1 hitting its minimum. That's a little bit too linear. What's going on here? Did I do that right? Yeah, 4 pi, 0.7, and then, yeah, halfway between is the 0.8. Okay. Yeah, that's... Why is it looking so linear? What am I doing wrong? Am I missing a value here? These ones did not show up that linear earlier. Well, I must just be messing up somehow. Well, whatever. We'll keep rolling with it. And then let's see. Let's see, halfway between here. Start going down. Start going down. And then it's at a half, and then it will be at 0. Yeah, those ended up not looking right at all.
That second one should be in space, shouldn't it? Shouldn't be on the line.
This one here?
It's not a full square over whatever.
No, this one is a full square over. It lands on 4 pi over 3. These ones are kind of like these ones here, where they're actually at the pi over 2 marks sort of thing. Yeah, it was all.
Is it supposed to look like that top one?
It is. It is. Clearly, I am just not good at plotting these points upside down. But it looks something like that. 0.866, yeah. Yeah, somewhere around there. I'm going to show you a digital version of this graph in a moment anyway. And we're not ever going to actually graph these in this much detail by hand again. Typically, what we'll end up doing is hitting this point, this point, this point, this point, and this point, and then you would just kind of draw a smooth curve between those two, those 5 points, and they would not be. Try not to make them perfect semicircles. Recognize that it kind of is real steep at the beginning and then gradually, slows down in steepness. So that's what we'd typically be doing. But what I want to point out is this function is periodic, right? So after 2 pi, I expect that it's going to jump up to a half again, right here, and it's going to actually start repeating this pattern again. All right, is what it would end up doing. And the same thing in this direction. It would actually be going down and repeating the pattern from over here. So sine is a periodic function, and let's actually graph it electronically, like so. Here we are. So you can see my graph of y equals sine x. Let's see, line style, medium right here. And so you can see that it actually would repeat. If I delete it and regraph it, it'll give us more versions of it. So you can see that it's repeating every 2 pi units. It goes through one up and down cycle, right? Up and down, there it is, up and down, like so. And it actually does the same thing in the other direction too. If I delete this and graph it again, you can see that it's repeating in all of those ways. So it's a very periodic function. This is called a sine wave sometimes. And sine and cosine functions, because we'll graph cosine in a moment, are actually often used to model all sorts of interesting activities, such as lunar cycles, tidal cycles, temperature often follows patterns like this throughout day and night, sort of things like that, as well as seasons. So these functions are used to measure all sorts of real-world data as well. So it's kind of really, really good, powerful stuff. So let's talk about just some of the properties of sine real quick. Let's rattle off some properties. Of y equals sine x. And we'll look at our graph to figure some of these out. So first of all, what is the period? How long does it take to repeat one full cycle? 2 pi. All right? So the period for sine is 2 pi. Let's see. What is the domain? Domain is the set of all x such that what values of x are allowed to be plugged in here? It goes all the way to infinity, all the way to negative infinity. There's no holes in the graph. So it's everything. Set of all x such that x. It's just everything. What is the range of the function? R is the set of all y such that, well, this one's a little bit more restricted. What's the highest it goes? 1. What's the lowest it goes? -1, right? So my y values are just bouncing back and forth between -1 and 1. So it's the set of all y such that -1 is less than or equal to y is less than or equal to +1. All right? Now, question. Where are the x-intercepts for the sine function? It's at 0. It's at pi. It's at 2 pi. Where's the next one going to be? 3 pi, and then 4 pi, and then 5 pi, or negative pi, and negative 2 pi, and negative 3 pi. So the x-intercepts actually occur every pi. So notice the x-intercepts occur within half of a period, right? It actually hits it more than that. So x-ints occur at all, I guess I'll call it n pi, where n is an integer. and is an integer. All right, and we'll have n pi is where that's occurring. Let's see, 5, here we go. What is the y-intercept for y equals sine x? 0, it's crossing at 0, right? And there's only one y-intercept. Let's see, what is the maximum value and where does it occur? Maximum value is 1, and it occurs at pi over 2. Where's the next maximum value going to be? Or how far over would it be? The period, which is 2 pi is the period. So if I add 2 pi to this, I'd hit another maximum. If I add 4 pi to it, it'd give me another maximum, or 6 pi. Or if I subtract 2 pi from that, I'd land at another maximum. So the max is 1 and occurs at pi over 2 plus 2 pi n, right? Where n is an integer. Right, so if I just keep adding 2 pi's or multiples of 2 pi to that, that's going to give me all the maximum locations. And similarly, what is the minimum value and where does it occur? Minimum is, what's the minimum value? You can tell me that much. -1. And let's see if we can figure out where they occur. Because there's infinitely many of them, technically. All right, it occurs at 3 pi over 2. How far is the next one away? 2 pi, whether adding or subtracting. And then the next one after that is another 2 pi away from that one. Or any multiple of 2 pi that I add to 3 pi over 2 is going to give me another value. All right, so it occurs at 3 pi over 2 plus 2 pi n, where n is an integer. All right, all sorts of crazy stuff going on that we can figure out. Now, having a graph of sine, you're actually able to kind of, maybe figure out, like, for instance, if I wanted to know when is sine equal to a half, all right, if I had that question. We've kind of been able to answer that using, trig inverses and stuff like that. But here, if I want to know when is sine equal to a half, I can see that it's going to occur here at pi over 6 and here at 5 pi over 6. It doesn't occur, notice, here or here. All right, so it's not at those locations, but it should hit again over here, right? 2 pi units away from this. And then also 2 pi units away from that. So I could actually end up finding, using the graph to answer some of those questions. Now, for sake of time, I'm going to compute the graph of cosine for us. We could do it the same way by hand if we wanted, making a table and figuring it all out. What do you think the period of cosine is going to be? It's actually also going to be 2 pi because it's got the same kind of coterminal nature with its angles. So let me show you cosine on this same graph. So graph of cosine x. Let me change the color here a little bit. And the line style medium. And the line style, we'll make it dashed. So here's cosine of x, right? Now, what is cosine at 0? Right, cosine is 1 at 0, right? In the unit circle at 0, the x, right, that's at the point 1 comma 0, cosine is equal to the x, cosine is 1. So notice cosine starts at 1. It drops down to 0 at pi over 2, or 90 degrees. It drops down to -1 at pi, or 180 degrees, and it goes back up to 0 at 3 pi over 2, or at 270, and then it goes back up to 1 at 2 pi in one full period. So notice that these are very similar graphs. They're so similar, in fact, that they're just like a horizontal shift away from each other. Okay? They're the same shape in all ways. They're just shifted, okay? Also, when are sine and cosine equal to each other? When do they cross? At pi over 4. And what's the value? What x value is that? What does pi over 4 mean in degrees? Right, it's the square root of 2 over 2, right? Is the ratio, and that occurred at 45 degrees or pi over 4 radians, right? And on the hand trick, remember that's when they were equal to each other, and we see that occurring here graphically where they cross. And the same thing occurs over here, negative root 2 over 2 over in the, this would be quadrant 3 where that's occurring. So all sorts of stuff that you can relate to these is really interesting. It's going to require you to be familiar with the values of sine and cosine. So you still need to know your hand trick. You still need to understand reference angles, coterminal angles. Now we've thrown in radians in the mix. And with these graphs, I mean, I don't know if you guys would have anticipated something, as interesting or beautiful and curvy and whatnot like this to come out of sine and cosine. All right, and these are periodic functions, right? And they're used to model all sorts of things in the real world. So they're actually very powerful. We'll be spending a lot of time on these for the rest of the chapter. So thanks for watching, Internet friends. Have a great day. Bye-bye.